Hello, everyone. Today I will be talking to you about using electron spin resonance spectroscopy for insight of different copper complexes. First, I'll start off with some background, starting off with the biological importance of copper. As copper is an essential nutrient for all aerobic organisms, which harness the energy from cycling between cuprous and cupric states is harnessed by these organisms for many biochemical processes. The free ion form of copper is actually toxic and can participate in fenton-like chemistry to produce hydroxyl radicals that are also extremely toxic. So organisms have complex biomechanisms that bind free copper to proteins. One of the amino acids that is most commonly found to bind to copper is histidine. It is one of the strongest metal ion coordinators in proteins, and it has an imidazole group that contains two nitrogens that copper can bind to, which makes it one of the most common ligands of copper complexes. And ESR can tell us of the structural details of these different complexes and give insight to the coordination environment that they're in. So some fundamentals of EPR or ESR, I'm sorry. Electrons have a fundamental charge and a motion around an axis that allows them to act as small magnets. And in a normal setting, the spin and magnetic moments of electrons are pointed in random directions. But when an electric field is applied, it aligns the electrons in either a parallel or anti-parallel fashion, where parallel is the lower energy alignment. And the energetic separation of these two states is known as Zeeman splitting, shown on the right here in this diagram. And the energy between these two states is simplified out to be the G factor times mu sub B times the magnetic field, where G is the spectroscopic splitting factor. Mu sub B is the Bohr magneton for an electron, and B is the applied magnetic field. And the transitions are possible from the parallel to anti-parallel state and can happen when the electromagnetic radiation is equal to G mu sub B times B over Planck's constant. To observe spin transitions, the sample is placed in a resonant cavity of the ESR, and microwaves of a fixed frequency are produced. A transverse magnetic field is then applied and gradually increased until the sudden drop in energy from the cavity. And this sudden drop represents the absorption of the energy by the complex and the corresponding transition from parallel to anti-parallel. There's also an interaction between the nucleus and electrons that affect the Zeeman splitting and the spectra, where the resulting absorption energy of the electron will be split into 2I plus 1 spectral peaks. And the simplified energy for the two spin system is this electron term plus the nuclei term plus the A constant, which is called the hyperfine coupling constant, times the MS and ML values. There are four possible combinations of MS and ML values. And there are two possible ESR resonance transitions that are separated by the hyperfine coupling constant. The four possible combinations are listed down here, and they represent the E1 to E4 transition and the E2 to E3 transition. And you can see on the right of that energy diagram, the peaks are separated by the hyperfine coupling constant. So the hyperfine coupling constant indicates this time spent near the nuclei, meaning how strongly the orbital is held to the nuclei. And the G factor tells of the electron spin momentum or the electron angular momentum. So these factors are inversely proportional and vary depending on the electronegativity of the ligands in the copper complexes, and they can be used to determine the arrangement of the ligands around the central atom. So I'll quickly go over the experimental procedure. My hypotheses were that the ligand arrangement that has the most pi bonds will have the highest G value because the G value is a direct proportion relating the overall magnetic moment to the angular momentum of electrons. The angular momentum of an electron increases with the energy. So the complex with the most pi bonds rather than sigma bonds will have the largest G value. And the most my second one is the most electronegative ligand of the complex will have the smallest A value. The A value is a measurement of how strongly an electron is held at the nuclei. And because more electronegative atoms hold their electrons more tightly, they will have a smaller A value. These are the three samples that we analyzed: diamidazole copper 2 diperchlorate, bis-2 methyl imidazole copper 2 diacetate, and tetrachizimidazole copper 2 sulfate. And these were all compared to DPPH, which was used in our calculations. Each of the three samples were synthesized with certain ratio. Sample 1, 25% glycerol, 75% sample. Sample 2 is 25% glycerol, 25% chloroform, and 50% sample. And sample 3 is 25% glycerol and 75% sample. The DPPH sample was already prepared and sealed in the capillary tube, and that was run first to get a baseline of the center field. And each sample was then transferred into EPR tubes covered with parafilm to mark how far down to put the tube into the ESR machine, so nothing gets broken. So my results are the spectra. On the left is DPPH with the peaks marked and the field where the transition occurs, where it crosses the x-axis. So sample 1 actually had a little bit of a funky spectra. It shouldn't have this dip here, but I essentially ignored that because it's the only spectra I have. And I counted this peak as the fourth peak and this point where it crossed the x-axis. So next, sample 2 is on the left and sample 3 is on the right, with all of their peaks marked and their x-axis, x-intercept also marked. And here's a table of the peaks and the G values. And we will talk about the meaning of these later. And the A values are reported on the bottom. How I calculated the G and A values. So the G value for the DPPH must be calculated to calculate the sample G values. So I calculated that, and to calculate the sample values, you multiply the G value of DPPH times the center field value of DPPH divided by the center field value of the sample. And the A value is just one peak minus its other, and the average was taken of those. And the transition, the energy difference for DPPH was calculated to be 6.33 times 10 to the negative 24 joules. And the Boltzmann distribution was also calculated, which I will talk about later. Actually, right now. So the two factors that affect the G value is electron delocalization and ligand electronegativity. The electronegativity of the ligands tells how strongly the electron is held to the nucleus. So the larger the electronegativity, the larger the G value. But resonance also contributes to that due to the increased angular momentum from delocalization. And the coupling constant A decreases with increasing delocalization. And so this goes back to my hypothesis, our hypotheses. So our results show that sample 2 had the largest G value, which disproved hypothesis 1 because sample 3 should have had the largest G value. But this can be attributed to sample 2's ligand, which was the acetates, because they have a larger electronegativity, because acetate is oxygen-based while the imidazoles were nitrogen-based. So oxygen obviously has a larger electronegativity than nitrogen. So this could be the reason that sample 2 had a larger G value. But if you recall, the G values for sample 2 and sample 3 were actually very close, within 0.001, 1/1000th of a G value. So they were very close. And sample 1 has the largest A factor, which confirms hypothesis 2, that the coupling constant decreases with increasing localization. So sample 1 has the least delocalization, so it had the largest A factor or A value. And then the change in energy value of dppH was calculated. So there could be a calculation of the Boltzmann distribution. And this is a necessary calculation because there has to be a larger population of the ground state in the ground state than the first excited state for ESR to be completed, because there needs to be a favorable transition to be observed. So the Boltzmann distribution was slightly over 1, meaning that the population in the ground state, confirming that the population in the ground state is larger than the population of the excited state. But that's it. Thank you for listening.